Hello, hi, good morning everyone. Myself Nishita from Computer Science Engineering in Artificial Intelligence and Data Science in Srinivas Ramanujan Institute of Technology. Today my topic is about the Clausius-Mossotti equation. Let us see the Clausius-Mossotti equation. First we discuss about the introduction on Clausius-Mossotti equation, the historical background, basic concept and mathematical formula, then derivation of overview, applications of the equation, finally limitations and assumptions, relation to other theories, then we finally discuss about the conclusion of this equation. Now we discuss introduction on Clausius-Mossotti equation. The Clausius-Mossotti equation relates the dielectric constant of a material to its molecular polarizability. It provides a microscopic understanding of how molecules respond to an electric field. This equation is fundamental in the study of dielectric properties of the material. Now we discuss about historical background on the Clausius-Mossotti equation. The equation was independently developed by Rodolfo Clausius and Otto Mossotti in the late 19th century. It was initially used to explain the dielectric properties of gases and liquids. Over a time, it has become a key concept in condensed matter physics and material science. Then we discuss the basic concepts of Clausius-Mossotti equation. The dielectric constant measures a material's ability to polarize in response to an electric field. Molecular polarizability describes how easily an individual molecule's electron cloud can be distorted. The Clausius-Mossotti equation connects these two properties through the molecular structure of the material. Then we discuss about mathematical representation of the Clausius-Mossotti equation. This is the mathematical representation of the Clausius-Mossotti equation. Here, epsilon r is the dielectric constant and is the number density of molecules. Alpha is the molecular polarizability. The equation assumes a spherical isotropic distribution of molecules within the material. Then now we discuss about the derivation part of this equation. Consider an elemental solid dielectric material of the dielectric constant epsilon r. Let n is the number of atoms per unit volume of the material and mu is the atomic dipole moment. Therefore, the dipole moment per unit volume is equal to n into mu. Let E be the internal electric field. Alpha is the electronic polarizability of the atom. We can write mu is equal to alpha E into EI. Dipole moment per unit volume is equal to n alpha E into EI. Dipole moment is represented by P. Therefore, P is equal to n alpha E into EI. N alpha E moving to left hand side, we can write EI is equal to P by n alpha E. P is equals to epsilon naught into epsilon r minus 1 into E. Epsilon naught into epsilon r minus 1 is moving to left hand side. We get E is equal to P by epsilon naught into epsilon r minus 1. The expression for the internal field in the case of three-dimensional array of atoms is given by EI is equal to E plus gamma by epsilon naught into P, where gamma is the proportionality constant and also known as internal field constant. Substitute for EI and E values in the above equation. We get P by n alpha E is equal to P by epsilon naught into epsilon r minus 1 plus gamma by epsilon naught into P. Here both P by epsilon naught is the common, then P cancel. We get 1 by n alpha E is equal to 1 by epsilon naught into 1 by epsilon r minus 1 plus gamma. Consider the internal field in the material to be Lorentz field, that is gamma is equal to 1 by 3. These 1 by 3 values substitute in the above equation, we get 1 by n alpha E is equal to 1 by epsilon naught into 1 by epsilon r minus 1 plus 1 by 3, that is equal to 1 by epsilon naught into 3 plus epsilon r minus 1 by 3 into epsilon r minus 1. Then we get epsilon naught by n alpha E is equal to epsilon naught plus 2 by 3 into epsilon r minus 1. Rearranging the equation, we get epsilon r minus 1 by epsilon r plus 2 is equal to n alpha E by 3 epsilon naught. The above equation is known as Clausius-Mossotti equation. Then we explain derivation part of the overview. The derivation begins with the Lorentz local field concept, which considers the field experienced by a molecule inside a material. It relates microscopic dielectric properties to microscopic molecular properties. The derivation involves assumption of isotropic and uniform distribution of molecules. Then we can see applications of the equation. The Clausius-Mossotti equation helps the estimation polarizability of molecules from measurable dielectric constants. It is used in designing materials with specific dielectric properties for the electric and optics. The equation also helps analyze phase transitions and critical phenomena in the condensed matter systems. Next, we discuss the limitations and assumptions of the Clausius-Mossotti equation. The equation assumes non-interacting spherical molecules which may not hold for complex or anisotropic molecules. It is the most accurate and moderate densities where intermolecular interactions are minimal. Deviations occur in solids. Highly polarizable molecules are at high densities. Then we can see, okay, finally, I will explain about the conclusion of this equation. The Clausius-Mossotti equation provides a bridge between microscopic molecular properties and macroscopic dielectric behavior. It is a fundamental tool in material science, optics, and condensed matter physics. Understanding its assumptions and limitations is crucial for applying it accurately in research and applications. Okay, thank you.